Hello and welcome back to Mech Zone. Today we shall be starting with the second module of theory of machines, and that is vibration and stress analysis. However, vibration and stress analysis is a very important chapter because almost हर साल गेट में एक क्वेश्चन तो हमेशा गारंटेड होता ही है. जितने भी सेट बनाए जाते हैं गेट के लिए उस हर सेट में एक ना एक क्वेश्चन मोस्टली 2 नंबर का गारंटीड ही रहता है हमारे स्ट्रेस और वाइब्रेशन एनालिसिस चैप्टर में से. एंड वी शैल बी स्टडिंग दिस चैप्टर इन द मोस्ट सिंपलेस्ट मैनर एज वी कैन, and we will try to cover almost all the basics of this chapter, and we shall also be solving the different problems which have been asked in the different competitive examinations. Okay, so if we talk about what actually are vibrations, then they are to and fro periodic motions about their equilibrium position. It is defined as to and fro periodic motion about their equilibrium position. Okay, so it is a periodic motion. It means it is simply repeating itself after a definite interval of time, and equilibrium position के about ये to and fro motion करता रहेगा, and this is also known as harmonic motions, or we can also call them as oscillations sometimes. इन्हें हम sometimes oscillations भी कह सकते हैं. ओके, सो अगर हम देखें किसी भी वाइब्रेटिंग सिस्टम में, फॉर एनी वाइब्रेटिंग सिस्टम वी हैव मिनिमम 3 थिंग्स एंड मैक्सिमम 4 थिंग्स और components. Okay, so what do we mean by mean position or equilibrium position? So mean position, equilibrium position or zero position are actually synonyms of each other, and they simply correspond to the condition when the summation of forces is equals to 0 and summation of moments is also equals to 0, such that it is also known as reference point. Okay, it is also known as reference point. So what are the main 4 things? The first thing is the kinetic energy storing device. Kinetic energy storing device. The second is potential energy storing device. Actually, I am having a sore throat, so my voice may not sound to be very good, and it is generally having a stiffness, say S. Okay, then we have kinetic friction. Such that it is not equals to 0, and the reason why it is not equals to 0 is simply because due to relative motion. Okay, due to relative motion the kinetic friction is still not 0. The fourth is unbalanced forces are not equals to 0. Okay, actually these first 3 parameters are corresponding to the non-running vibrations. They are also called as non-running system vibrations. And all these 4 are actually constituting running system vibrations. Okay, running system vibrations. Now for example, if I draw graph for a sine wave like this, okay, so we see that this is the amplitude from, or amplitude means the maximum displacement from the mean position. So since it is having a to and fro nature, and therefore it is a vibration. This type of motion can be termed as vibration. Okay, if we draw a cos wave, then in the cos wave also we are having the same type of to and fro motion, and hence it is also a type of vibration. So this is to and fro vibration, and this is also a part of vibration. But if I consider the example of sine square wave, such that I draw the graph. So sine square wave graph is like this. Okay, sine square wave graph is like this, and since it is not undergoing a to and fro motion मतलब एक्सिस के ऊपर भी होना चाहिए और एक्सिस के नीचे भी होना चाहिए, यहाँ पर सारा का सारा मोशन सिर्फ एक्सिस के ऊपर ही हो रहा है, hence it is not a vibration, and this graph was actually drawn for sine square wave. This is actually for sine square wave. Now we will start with the topic of natural vibrations. Okay, now we will start with the topic of natural vibrations, and in case of the natural vibrations, kinetic friction is actually considered to be zero. So the vibrations in which there is no friction at all, as well as there is no external force after the initial release of the system, then such type of vibrations are called as natural vibrations. Okay, for example, if from a point we have suspended a mass m such that S has been given the stiffness of the spring, and this was the equilibrium position, and we apply a force, or if even we do not apply a force, this mass will be displaced a little bit downward, say by an amount x. Okay, so let us assume that initially xi is the displacement from the natural length due to this weight mg. Okay, xi क्या है? xi हमारा इनिशियल डिस्प्लेसमेंट है जो कि इस वेट के कारण प्रोड्यूस होगा. सो इट इज द इनिशियल डिस्प्लेसमेंट from natural length due to mg from natural position. Okay, so this is actually the mean position. So if we write down the equation for equilibrium, we will get mg is equals to s into xi. This would be the equation for equilibrium. Okay, now what is done? A disturbance is created in the downward direction. Okay, a distance has been created in the downward direction. Now what I will do is I will try to draw down the FBD such that one force mg was already acting downward, one disturbing force is also acting downward, such that in the upward direction we have s x plus xi. Xi was the initial displacement and x was also added to it when it was displaced by an amount x. So downward direction is the direction for disturbance that has been created in the system. Okay, now from the Newton's second law, we have m into a is equals to minus s into x. Okay, because in the direction of the disturbance and forces opposite to the direction of disturbance is acting. तो ये नेगेटिव क्यों हो गया? ये नेगेटिव इसीलिए है क्योंकि यहाँ पर ये जो हमारा MA है, it is actually taking in the direction of disturbance, but the forces are acting opposite to the direction of disturbance and hence it is taken as negative. क्योंकि disturbance तो हम नीचे कर रहे हैं लेकिन spring force कहाँ लग रहा होगा? ऊपर लग रहा होगा, इसीलिए हम यहाँ से इक्वेशन क्या मिल जाएगी? MA is equals to minus SX. Okay. Now I will discuss a very important principle which is called as D-Alembert's प्रिंसिपल। प्रिंसिपल की स्पेलिंग में लास्ट में PLE आ रहा है, तो ये सिद्धांत वाला प्रिंसिपल हुआ। अगर मैं PAL लगा देता तो वो प्रधानाचार्य हो जाते, स्कूल वाला प्रिंसिपल। तो इंग्लिश में ये सब चीज़ें भी हमें बहुत ध्यान देनी पड़ती है, क्योंकि कभी कभी लोग PAL भी लिख देते हैं झटके में, तो वो चीज़ गलत है। हाउएवर वो गेट से तो कोई मतलब ही नहीं है किसी भी कॉम्पिटिटिव एग्जामिनेशन में। लेकिन अगर आप किसी सब्जेक्टिव एग्जाम को दे रहे हैं और उसमें अगर आपने लिख दिया और बाय चांस जो करेक्शन कर रहा है उसने नोटिस कर लिया, तो हो सकता है वो थोड़ा सा रुष्ट हो जाए। ठीक है, यहाँ हम क्या करेंगे, हम यहाँ पर एक इनर्शिया फोर्स लगाएंगे। वी विल अप्लाई एन इनर्शिया फोर्स सच दैट इट इज ऑलवेज प्लेस्ड ऑपोजिट टू द डायरेक्शन ऑफ डिस्टर्बेंस। दिस इज ऑलवेज प्लेस्ड ऑपोजिट टू द direction of disturbance. Ab, if you look in the above system, the disturbance has been created in the downward direction, so this Fi, that is the inertia force, will be applied in the upward direction. And I redraw the diagram, that is Sx and upward force Fi, which is equals to m into A, and a downward force would be acting mg. Okay, so according to the D-Alembert's principle, ma plus sx, it is equals to 0. Actually mg would not be here, mg is not here. Okay, so it is equals to 0. And acceleration, as we all know, acceleration is equals to dv upon dt, and velocity is dx upon dt. So acceleration can be simply written as x double dot and velocity can be simply written as x dot. So we have mx double dot plus sx is equals to 0. We will divide the entire equation by m, so we will get x double dot plus s by m, x is equals to 0. So this actually becomes the equation of the neutral system. Equation of the neutral system. Okay, this becomes the equation of the neutral system. And the solution would be, the solution of such type of equation can be in the form of x is equals to r sine under root s by m t plus phi, where in such type of equation r is actually the amplitude of vibration and r and phi are generally constants. Okay, these are constants. तो देखिए यहाँ पर एक डाउट आ सकता है कि सर आपने पहले तो mg लिखा फिर इसे काट क्यों दिया। एक्चुअली देखिए यहाँ पर हुआ क्या था, अगर इस वाले केस में भी देखें तो mg sxi जो होगा, इनिशियली ये जो चीज थी इट वाज बैलेंस्ड बाय mg। ठीक है, तो यहाँ पर जब हम इसके इक्विलिब्रियम की हमने लिखा था पोजीशन, तो वी वुड राइट, एक तो mg नीचे की ओर फोर्स लग रहा है, ठीक है, sxi इज इन द अपवर्ड डायरेक्शन और m into a, this was also in the downward direction. So अगर हम लिखें the summation of upward forces equals to summation of downward forces, वहां से हमें ये चीज ऑब्टेन हो जाएगी। सिमिलरली यहाँ पे हमारा क्या होगा, mg तो नीचे एक्ट करेगा sx प्लस sxi, तो ये sxi और mg कैंसिल आउट हो जाएंगे, इसीलिए आई हैव रिटन दिस टू बी 0। और m into a तो आपका ये लग ही रहा था और mg आपका नीचे लग रहा था और नीचे ही की डायरेक्शन में आपका डिस्टर्बेंस भी था। तो m into a is acting in the upward direction and sx is also acting in the upward direction, और नीचे कोई भी फोर्स नहीं लग रहा है because this mg has already been cancelled by sxi, इसीलिए आई हैव रिटन ma plus sx is equals to 0। तो ये हो गया हमारा। तो क्योंकि यहाँ पर हमें साइन फंक्शन मिल गया, so because or since sine function is achieved, which is a harmonic function, so this equation actually represents a case of vibrations. Okay, this case actually represents the form of vibrations. So now vibrations with natural frequency omega n. Now we will study a topic where vibrations will be taking place with a natural frequency omega n. Now let us say that vibrations are taking place, vibrations with omega n, where omega n is the natural frequency of vibration and omega n is equals to under root s by n, and the unit would be radian per second. Okay, now we will compare it to the wave equation. Okay, we will compare this thing with the wave equation such that the natural time period would be equals to 2 pi by omega n and frequency would be equals to omega n upon 2 pi hertz. Okay, so this is actually a linear form. This is actually a linear form. Okay, now what we will do is, in the equation that we have written for r and phi, actually जो हमने equation लिखा था वहाँ r and phi they both were considered or they both were constants. Okay, so at t is equals to 0 की बात करें, then we have x is equals to x naught and x dot, that is the velocity, was also 0. तो उसके corresponding r की वैल्यू निकाल लेंगे और phi की वैल्यू निकाल लेंगे. ये था हमारा पहला कंडीशन. दूसरी कंडीशन क्या हो सकती है? At t is equals to 0, x can be equal to 0 और x naught can be equals to v naught. So यहाँ से भी r की वैल्यू निकाली जा सकती है और phi की वैल्यू को कैलकुलेट किया जा सकता है. Third is, at t is equals to 0, we can have x is equals to x naught and x dot is equals to v naught. So from here also we can find out the value of r and phi. So finally, if we look, the equation of natural vibrations becomes omega x double dot plus omega n square x is equals to 0. This is actually the final equation of natural vibrations. Okay, now for example, we have been given a system like this. A spring is attached to a mass m. So what would be the natural frequency of vibration? It would be under root s by m. Okay, so यहाँ पर हमारा जो mg था, it was balancing sxi, that was the deflection, initial deflection. Now for example, if we have a system like this, ओके, तो यहाँ पर हमारा जो xi होगा इनिशियल डिफ्लेक्शन, तो यहाँ पर हमारा क्या हो जाएगा? 0. ये हमारा स्टिफनेस दिया हुआ है s, तो यहाँ पर भी नेचुरल फ्रीक्वेंसी वुड बी इक्वल्स टू अंडर रूट s बाई m. इस केस में भी ओमेगा इज इक्वल्स टू अंडर रूट s बाई m, यहाँ पर भी इट इज इक्वल्स टू अंडर रूट s बाई m. Okay, now if we have another configuration, say we have a system like this. This is a wedge having an angle theta. This is mass m. So here mg sine theta is sxi. So this initial deflection into the stiffness is actually balanced by mg sine theta, and hence it gets cancelled out while we are writing the FBD or the free body diagram equation. And इस केस में भी omega is equals to under root s by m. So this is a very important formula. तो आप इसी फॉर्मूले को याद रखिए. कन्फिग्रेशन चाहे कैसा भी आ रहा है, अभी तक तो हमने यही देखा कि हमारा फॉर्मूला हो गया अंडर रूट s by m. Now next topic we will start with the combination of springs. We will now start with the combination of springs. Okay, the springs can either be attached in series or they can either be attached in parallel. So in case of the series, what we will have, the springs are attached end to end connection like this. Say this is a mass M, stiffness is S1, stiffness is S2. So equivalent stiffness S1 upon S equivalent is equals to 1 upon S1 plus 1 upon S2. Actually this is the formula for the resistances that we have studied when they were connected in parallel. तो इससे उल्टा याद रखना है कि रेजिस्टेंस पैरेलल का जो फॉर्मूला है वही हमारा स्प्रिंग का सीरीज में फॉर्मूला है. और यहाँ पर क्या हो जाएगा, यहाँ पर आपका लोड जो होगा, लोड सब में सेम हो जाएगा. ठीक है, लोड इन ईच स्प्रिंग वुड बी सेम इफ दे आर कनेक्टेड इन सीरीज. एंड नाउ फॉर एग्जांपल दे आर कनेक्टेड इन पैरेलल. ओके, दिस इज S1, दिस इज S2. सो यहाँ पर रिवर्स फॉर्मूला लगा दीजिए. रेजिस्टेंस का सीरीज का फॉर्मूला होता था वो यहाँ पे इसके पैरेलल का फॉर्मूला हो जाएगा. तो S इक्विवेलेंट इज इक्वल्स टू S1 प्लस S2. तो यहाँ जो ओमेगा हो जाएगा, ओमेगा इज इक्वल्स टू अंडर रूट S इक्विवेलेंट अपॉन M. यहाँ पर भी जो ओमेगा n का फॉर्मूला हो जाएगा नेचुरल फ्रीक्वेंसी का अंडर रूट S इक्विवेलेंट बाय M. तो फॉर्मूला तो वही लग रहा है, बस सिंपली S इक्विवेलेंट निकालने का तरीका बदल जाएगा व्हेन दे आर कनेक्टेड इन पैरेलल और व्हेन दे आर कनेक्टेड इन सीरीज. हालांकि जब ये कनेक्टेड पैरेलल में कनेक्ट होंगे दोनों में डिफ्लेक्शन क्या आ जाएगा, द डिफ्लेक्शन इज सेम इन बोथ द स्प्रिंग्स फॉर पैरेलल कनेक्शन. ओके, नाउ वी कम टू अनदर इंपॉर्टेंट टॉपिक, दैट इज इफ वी आर कटिंग द springs. Say the springs are being cut into a desired length. So we first have to remember this thing, that stiffness is inversely proportional to the length of the spring. जितना छोटा spring होगा उतना ज़्यादा उसकी लेंथ जितना कम होगा उतनी ज़्यादा उसकी स्टिफनेस होगी, और लेंथ जितनी ज़्यादा कर देंगे स्टिफनेस उतनी ही कम हो जाएगी. फॉर एग्जाम्पल we have a spring like this and we cut this spring into two parts, say half. Okay, so the stiffness for this part would be 2s and the stiffness for this part would also be 2s. Okay, now say for example we have a spring, and what we have done is we have bisected this in two parts such that the above part is m and the lower part is n. The stiffness of this part would be m plus n upon m into s, and the stiffness would be m plus n upon n into s for this part. Now say for example we have a spring. Okay, we have trisected it into three parts such that this is m, n and this part is p. The stiffness of this part would be m plus n plus p upon m into s. This part would be m plus n plus p upon n into s, and for this part it is m plus n plus p upon p into s. So by this we can find out the effective stiffness of the parts which have been cut from the main spring. Okay, so with this we come to the end of this lecture. I hope you are all enjoying our lecture, so do give us your valuable feedbacks. However, I think the section of governors and cams, gyroscope and cams are left. We will be covering that simultaneously, and प्लीज़ सब्सक्राइब कीजिए हमारे चैनल को और हमारे को बताइए, अपने प्रॉब्लम्स हमसे शेयर कीजिए, और आप सारा का सारा स्टडी मटेरियल एब्सोल्युटली फ्री ऑफ कॉस्ट डाउनलोड कर सकते हैं हमारे चैनल से. वो हमारे हर वीडियो के डिस्क्रिप्शन सेक्शन में दिया होता है, और आप हमारे चैनल के बारे में अपने फ्रेंड्स और कोलीग्स को भी बताइए सो दैट दे आर ऑल्सो बेनिफिटेड, बिकॉज ऑल द स्टडी मटेरियल इज अवेलेबल एब्सोल्युटली फॉर फ्री ऑन दिस चैनल. सो थैंक यू सो मच फॉर टुडे.